Okay, let's get started. Hello, everybody. My name is Eric, and I'm a graduate student at MIT right now, finishing my 5th year in the biological engineering department. And it's my pleasure today to show you through some of the fundamentals of network analysis. So before we get started, just a quick show of hands. How many of you are feeling good this morning? Okay, awesome. We want some positivity in the room. If you haven't already, please download the GitHub repository, either git clone or download the zip file. If you are not planning to code today, that's completely fine. I'd encourage you then to pair up with someone who's at a computer terminal so that you can actually try out some of the hands-on exercises. A note about today's tutorial, I'm not going to talk much. I have 5 minutes worth of lengthy content, and then there's a lot of you trying out some of the exercises that are inside there. And another note is that I'm used to having this tutorial be 3 hours long, and so usually what I've done is I've interspersed little bits of me talking with you coding. And then I've waited for about 80% of the class to say, OK, I'm good, and then we'll move on. So a note about that. It's perfectly fine if you don't finish the activity. The idea is that you've been thinking about it and you've tried something. Secondly, because we only have an hour and 40-ish minutes, I'm going to reduce that 80% threshold to 40%. So if I see 40% of people more or less done, I'm going to move on. And like I said, if you didn't finish, don't worry. It's totally OK. Third thing about the format, the structure. If you look inside the GitHub repository, there usually, for most notebooks, there are 2 versions. There's an instructor version, and then there's a student version. Obviously, in the instructor version, all the answers are coded there. If you follow along with the instructor version, all right, I can't do anything. But if you want maximum benefit, please follow along using the student version. All right, I'm going to give everybody just a very, very quick quiz, because you're going to see this coding pattern a lot. What's a plausible data structure for my favorite things and S? Do we have any volunteers? Dictionary for S. Yep, and my fave things is probably a sum iterable a list. OK, great. If you all could get that question, that means you're good to go for this class, because that's really the level of Python that's required. Apart from also understanding, functions, what they return, really you're going to see a lot of this coding pattern. If you read the README or if you read the preface notebook, you can use the checkenv.py script, so Python checkenv.py, and it'll check your environment. It's something I threw up last night or something just to make sure people could make sure everything's OK. There's also an environment.yml YAML file inside there. And so if you use conda env, we all love Anaconda. We all love continuum analytics. And so if you use conda env, you can use the environment.yml file. And I want to give credit to Dan for pointing out the errors in my YAML file this morning. All right. So all of that administrative stuff that I went through, downloading the repo, checking your environment, if you want to take the next 5 minutes of me talking to just focus on that, no problem. Go ahead and do that. In the meantime, I'm going to talk through some of the motivation for some of the content in this tutorial. So you all are here to learn about the fundamentals of network analysis. And what we're going to do is we're going to go through some of the basic algorithms and mostly algorithms, really. We're going to go through some of the basic algorithms in network analysis, as well as things to look out for in a network. So I want to get some definitions out of the way first. Networks are a kind of data structure. In computer science terms, they're also called graphs. And their definition is extremely simple. It's circles and lines. Or in other words, in more technical terms, it's nodes and edges. Nodes represent entities. They could be airport stations. They could airport terminals. Sorry. They could be transportation links, hubs. Sorry. And then edges represent the relationships between these entities. So, for example, we might talk about an airport air transport network where we've got planes flying from terminals to terminals. So, one thing that I'm hoping that you will take away from today's tutorial is that you'll learn to think in terms of edges and not in terms of nodes. In other words, I'm hoping you'll learn to think in terms of relationships between entities and not just the entities themselves. We're used to basic stats, right? Basic stats talks about how many football players are what's the distribution of football players in high school football teams. But we rarely talk about the friendships between, or the matches that are played between these football teams, right? Or we don't talk about the people and their interactions on the team and how the relationships and interactions can give rise to winning or losing stats. So I'd like to, one of my goals for today is to have you go back thinking in terms of relationships between entities and not just the entities themselves. And to take a quote from a professor at the Harvard School of Public Health. It's not published anywhere, so you can't verify it. You just have to take my faith on it. He mentioned it at a network analysis seminar that I had attended. Basically, the heart of a network lies in its edges and not in its nodes. So I hope you'll ponder over that throughout today's tutorial. There are generally two types of networks because relationships can be unidirectional or they can be bidirectional, or they can not have any direction. And so we have directed and undirected graphs. And in today's tutorial, we'll only be dealing with the undirected version because it's the simpler version to deal with. So I gave some examples of networks just now. There's air transportation networks. There's, Facebook is a social network in which the nodes are users, and then the edges are whether users are friends with each other. Just wanted to throw this question out there to everybody. What other networks have you all heard about? Any volunteers?
Networks for epidemiology, spread disease.
Disease spread networks, so contact networks or the actual transmission networks. Absolutely, that's right up my alley actually. Hyperlink networks, so links between web pages. Anything else?
Balance sheets of financial institutions.
Balance sheets? How is that a network? That's an interesting one. I've never heard of that.
So they're counterparties, financial counterparties to each other.
Ah, okay.
By looking at the balance sheet is the node and counterparty relationship is the link. You can do
okay.
almost epidemiological study of financial contagion risk.
Wow. Okay, that's the first that I've heard. It's really good. It's a really good example. So in today's class, we'll try to, what I'm going to show you is also a glimpse of how to model a problem as a network and how to extract useful information from that network of stuff. Specifically, by the end of this tutorial, practically speaking, you should be able to use the NetworkX package to construct graphs in the Jupyter environment because we're all using Jupyter notebooks today. Secondly, you'll have a recognition of some common network visualization methods, so node link diagrams, heat maps, Circos plots, and hive plots. You should be able to implement basic algorithms to find structures and paths inside a network. And finally, and this is the most fresh content, it's also what I think the most exciting content, you should be able to do statistics on networks using hacker methods, right? And so I'll give you a little bit more background when the time comes. And as I was mentioning earlier, in broader terms, think in terms of interactions and think through statistical problems in network analysis. All right, so that's it for me talking on and on and on and on and on. We're going to get started with the coding challenges right now. So what I'd like you to do is open up notebook number 2. I'd like you to open up notebook number 2, and what we're going to do in this notebook is have you become a bit more familiar with the NetworkX API, all right? The function calls that are available to you and how you can use the NetworkX API to make queries on a graph. So for this tutorial, I've created a synthetic social network. It's not based on any real data. And we're going to use this synthetic social network throughout the class to explore all of that. So before we continue, just want to make a few points about how NetworkX represents networks, right? So NetworkX represents networks in terms of a graph or a directed graph object, all right? And under that object, there are two attributes. One is called node, and one is called edges. Edge, sorry. Nodes are dictionaries, so you'll use dictionary accessor methods quite a lot. Edges are also dictionaries, except they are dictionaries of dictionaries, if I'm not remembering incorrectly. It's either dictionary of dictionary or dictionary of dictionary of dictionaries, one of those two, all right? And so with edges, you'll be also using dictionary methods a lot. And so when you want to store an object, store an item as a node in NetworkX, you have to make sure that they are a hashable object. So strings, tuples, OK. Lists and sets, not OK. Generally, people use strings, integers, and stuff because they carry meaning that's human understandable. So in this social network, we're going to answer the following questions below. How many people are present? What's the distribution of attributes? How many relationships? And what's the distribution of number of friends each person has in the synthetic social network? All right, so let's load it up. If you could run this cell, g equals nx.read gpickle, and that will load the synthetic social network into memory, and it'll have the variable name g over there. All right, so just run that cell really quickly. So let's get started. Oops. Let's first understand how many people are present inside the network. So the function call for getting the list of nodes that are present is g.nodes. Oopsie, sorry. So if you could run this cell here, g.nodes, you will see that we've got 0, 1, 2, 3, 4, 5. And what g.nodes has done is it's returned a list of integers. And that's because the integers are the nodes inside the network, and g.nodes will return an iterable list. So what I'd like you to do now is to take 30 seconds to write a single line of code that returns the number of individuals represented. And when you're done, please just give a thumbs up. Okay, all right. Good, good, I saw it, all right. We wait for just a few more people. And if you're done, don't forget, please give the thumbs up. All right, so if you've got len g.nodes, great. If you assign it to some variable or something else, totally no problem. The point is, it's an iterable, right? So we can calculate its length. All right. If we then want to understand the relationships in the network, we look at the edges. And so NetworkX also provides an API for accessing the edge list that's present inside the network. And so we've got, so the edge list essentially lists every edge that's present inside there as a tuple, a two-tuple, in which you have, if it was a directed network, it would be source and sink. But if it's an undirected network, it would be just the two nodes that are linked together, with order not being important. All right, so likewise, take 10 seconds now to write a single line of code that returns the number of relationships present inside the network. And when you're done, please give the thumbs up. OK, saw you guys, saw you all. Any more? Good, I see you guys, see you all, good, very good. All right, so if you got len g.edges, great. That's, it should be, for the level of Python that we're dealing with in this class, I believe it should have been trivial. If it wasn't, that's no problem. Maybe the NetworkX API is a bit unfamiliar and what it's returning and stuff. Don't worry, with time and practice, this becomes something that is reflexive. All right. Networks can store metadata. So a node can have properties, right? I can have an individual. I can have that individual's age, and I can have the individual's gender, right? I can also have metadata associated with with the edges, right? So I can say if A and B know each other, I can store along that edge what date that friendship or that knowledge of each other was formed, all right? So in the NetworkX API, if you do g.nodes and you pass in the parameter data equals true, you'll get a two-tuple, a list of two tuples in which the first element is the node, and the second element is a dictionary of all of the metadata that's stored inside that dictionary, stored for that node, all right? So if you run that cell, that's what you'll get. What I'd like to give everybody now is a 2-minute coding challenge problem, which is to count the number of males and females that are represented inside the network. And as a hint, you may want to use the counter object from the collections module. Right, and I'm just going to flash this up here, because the coding activity is all present inside your notebooks as well. So I'm going to flash this up here so you can have at least a visual representation of what's being returned. And then likewise, when you're done, please give a thumbs up. OK, great. OK, I see more hands. Great. I see another one. I'm going to give you guys a hint of the, well, I'll just show the answer for now, and then I'll maybe talk through the answer, all right? So what we're doing is we're iterating over the nodes. Actually, you know what? I'm going to do a longer-winded version of this guy. So let's comment that out. So how one would do it in a non-list comprehension way would be to go m equals 0 and f equals 0, so male and female. And then we go for node in g.nodes, data equals true. Keeping in mind that now node is a two-tuple, we want to access the second element. We'd go node if node 1 equals, if node 1, and node 1 is a dictionary, so then we can use dictionary accessors. Then we do f plus equals 1, else m and m plus equals 1. And then we can print f and m. OK, very interesting. I must have had, I've added 2 people. It should be 15, 15, not 16, 16. And I've added 2 more people inside the network later on, and that's part of the API. So if you got 15, 15, that's cool. But a more compact way of doing it is to use a list comprehension. So I'm going to take this out. And if we take a look at this, we're saying we're unpacking the two-tuple that comes in for n, d, and g.nodes, right? So we're iterating over 2 tuples, so we can unpack the tuple in the for statement. And then we can access the biological sex of that individual. And then over here, because we're encapsulating it inside a list comprehension, we'll get a list of male, male, female, male, male, female, 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 male, male, female, right? And then the counter object will take that list of things and summarize it as male and female. And like I was saying, I added 2 individuals later on, so it's supposed to be 15 and 15. All right? So that's sort of this list comprehension way of thinking. I'd like you guys to start thinking in terms of list comprehensions as well. It's a very compact way to express what you're querying for inside the network. So likewise, edges can also store attributes I was mentioning earlier. So if you run the cell below, you'll get g.edges, data equals true. All right? And so inside this data structure that's returned, it's a list of 3 tuples where you have the 2 nodes as the first 2 elements. And then you have the dictionary of attributes that is the third element, right? And so that's this guy over here. And so there's a date that stores a date time object that stores what date, on which date these friendships or relationships were forged. So as the next, date time objects, just so that you know, they have attributes as well, and you can access their year, month, and day. It's just a little tidbit of information. All right, so as the next exercise, can you figure out the range of dates during which these friendships were forged? Likewise, again, I want you to think in terms of list comprehension. So try that out. And specifically, I want you to compute the earliest and the last date of these relationships. All good? OK, please give that a shot. And if you're done, please give me a thumbs up. OK. I'm using Python 3. So if you're on Python 2, I've created an environment.yaml file that should give you, that you can use conda env with. There's a README. Follow the instructions there. And if you're finding that you're falling behind a little too much, don't worry. Go and pair up with someone else who's got the right environment. The important thing is to talk through the problems. So how many people are done? Just to give a quick show of thumbs. OK, we'll wait a little longer. And if you're done, just give a quick thumbs up, right? So as I was mentioning, if you're struggling with the, there's instructor and student versions of the notebook. So if you're struggling, you want a hint, go ahead, look at the instructor version as well. Right? And that's fully applicable to this notebook plus all of the other notebooks that are up there. OK, how are people doing? So I'm just going to flash up the answer up there if you got something like that, or if, at the minimum, if you got 2002, 0520, and then 2011, 1104, then that's great. That's basically it. All right, and as just so that you know, right, just to let you know, we're also using the list comprehension coding pattern. This is a coding pattern I want to hopefully transmit to everybody. It's very useful for very compact queries on the network. All right, so let's continue on. We found out that there are 2 individuals that were not added. So that was why I had 16 individuals, 16 and 16, not 15 and 15. You guys don't have that just yet. So what I'd like you to do is to use the g.addNode and g.addEdge functions to introduce this data that I'm describing up here. All right, and I believe I have provided starter code, an example addNode and an example addEdge for you to model off.
AddNode would be an idempotent type operation. Like if you keep adding it, it doesn't have adverse effect.
That's right. That's right. So if the node is already present, it just silently overwrites that node that's present. OK, how many people are done? Can you give a thumbs up? All right, we'll wait just a few more minutes. Any new completers? Okay, okay, great. All right. So if you got this, perfect. And I provided a little example of how to access the metadata for a particular node. So if you know the node label, in this case it's 31, then cool. You can also do the same with edges. So if you do edge 31, 32, you'll get what's returned is the dictionary attribute, right? If you do, I think if you do 31, if you do edge 31, so you only provide one of the nodes in the edge, what you'll get is a dictionary of dictionaries. So you'll see the key is the other individual that it's connected to, and the date, and then the metadata that's associated with that as well. All right? Okay, and if you ran that cell, then cool, you should have an all test pass. If you got an all test pass, that's good. I didn't test for everything, but that's just a quick and dirty test function that you can use. So just a very quick note about tests. I am, I guess, a pseudo data scientist. I don't really know what you would call a PhD student doing analytics. We've all heard about testing your code, right? Testing your code, so writing tests, writing unit tests, doing automated, what is this, Travis CI, automate continuous integration, then you add in a py.test bash call inside there. Testing is good when you're writing code. Testing is also good for your data. If you're doing data analytics, you'll want to ensure the integrity of your data. Things that you expect to be true about your data should be true in the actual data that you get. If you're planning to log 10 transform something, you can't have things be negative valued or 0 valued. So you'd want to write a test for that particular column of data. And so writing tests is important. I've given a lightning talk on this. I'd encourage you to encourage you to check it out, see if it's of interest for you all. I think tests are a great automated written contract between you and your data, right? And if the data keeps changing, you'll want to write tests to ensure data integrity. Also, this thing about defensive programming, software carpentry has a great tutorial on that. I'm not going to mention any more except put that URL out there for you all. Okay, so I was mentioning coding patterns, list comprehensions. They're big, especially when you're doing with network data. You're doing recursion a lot. For things that are one level deep, use a list comprehension. Don't use a for loop, because if you're doing algorithms on networks, you're going to be using nested for loops, you're going to use a lot of recursion in networks. So as far as possible, keep your code compact. Keep your code compact. Basically, that's my message. I've listed out here things for your reference that you can reference in later notebooks or beyond this tutorial if you'd like as well. So iterating over nodes, iterating over edges. And like I was mentioning, if you're using a directed graph, if you're using an undirected graph, you'd use N1, N2, for example, in your list comprehension. Or if you're using a directed graph, you may want to choose your variable names in a way that is informative for yourself. So source and sink might be a better variable name instead. Okay, so the final part of this notebook is on drawing graphs. And I have no coding challenges there. I just want to quickly run through an overview of how you would draw networks. This, using nx.drawg, is the most common way that you'll see in academic papers, in online visualizations, etc. You'll see a hairball. And it's a hairball by the time you get beyond 30 to 50 nodes. If it's a small network, node link diagrams are OK. If you're going to talk about a 1,000 node network, please do not use a node link diagram. It ends up looking like a hairball. Instead, like I was saying, if you have nodes, if you have your network being small enough, you can enlarge the size of your node. You can add in visual labels and stuff with the NetworkX API. But like I was saying, please don't use it if your network is beyond 30 to 50 nodes in size. So another way of visualizing the network is to use a matrix. right? And so a matrix representation looks something like this over here, in which on the x-axis you list all of the nodes, and on the y-axis you list all of the nodes. And with a 1 or 0, let's say it's an unweighted network, with a 1 or 0, you can indicate whether a relationship exists or not. You'll notice that essentially either the bottom half of this matrix or the top half is sufficient to represent all of the data if it's an undirected network because they're symmetrical along the diagonal. If, however, you have a directed network where I may know you, but you may not know me, then you'll need the full matrix to represent all of the data, all right? Recently, I think, and by recently, it's with respect to network visualization history. Recently, there's been 2 innovations that I really like to visualize interactions and networks. And they are the Circos plot and the Hive plot. An undergrad that worked with me helped me implement the Circos plot in Python. Previously, there was no such thing available for Pythonistas, so we built on top of the matplotlib API. Oopsies. And we're able to create something like this, in which all of the nodes are ordered in a circle around, around the circumference of a circle, and then edges are drawn in this way between them, right? And so if you go online, circos.ca, so it's built in, it was invented in my homeland of Canada, in Vancouver, my home city. Woohoo, yes, thank you, Canadians. All right. So it's invented of circos.ca. You'll get to see some example visualizations. Circos plots were initially used for genome visualizations. They're a very highly aesthetic way of visualizing network data, right? Over here, you can see there are 2 nodes that are unconnected inside the network, and that should correspond exactly with what we see inside a node link diagram. So finally, let's try the Hive plots. And so again, nobody's implemented Hive plots for Python, so I wrote my own utility to make a Hive plot. The API is kind of ugly because I'm not really a programmer, so please forgive me for that. That said, it's on Conda, it's on pip. I haven't released Circos yet because we're still making a few more bug fixes over there. But if you take a look at that, this is the social network that we're visualizing over there. And what we've done is we've grouped. It's a rational way, in my opinion, of visualizing networks. You show the structure of the network with respect to certain properties that are inside that network. So if we group the nodes, we've got a group here and a group up there. We can look at the intergroup relationships and the intra-group relationships, all right? And we can get a visual feel for how the structure of the network is influenced by the metadata inside the network. All right, so yes? Yes, that's right. So that's a very good point. So if you want to visualize, if you're only interested in a Hive plot, if you're only interested in intergroup relationships, you wouldn't clone the axes. You'd have a single axis, so a blue axis and a red axis. And that would look very much akin to, say, you'd have those flat line things where you'd have arcs being drawn between nodes inside the network. So that would be akin to that. Now here, to look at the intra-group relationships, rather than drawing messy self loops on there, the way that it's done is one clones the blue axis and one clones the red axis, and now we're able to see the relationships within the red group and the blue group. All right.
So it sounds very interesting. Can you tell us one application or one case which this makes sense?
Yes. So let's see. What have I seen before? So I've seen protein interaction networks, right? And there are a gazillion proteins that are inside the body, and we know whether they are in contact with one another or not. Those proteins can be grouped by their general function. So for example, you can have things that are involved in metabolism. You can have things that are involved in sugar metabolism. You can have things that are involved in fat metabolism. You can have things that are involved in protein metabolism. And then you can ask, are these interacting with one another? Are these proteins that belong to disparate groups interacting with one another, or are they interacting more within their own group? All right? And I think the answer is they are interacting more within their own group. if you're interested in biology. Right. So that's one application. And here we have another where, so the core idea, the abstract idea is group your nodes and then see the relationships intra and inter group. All right? Okay. All right. So that's it for the introduction to the NetworkX API plus a bit of drawing networks. Yes?
I just you showed the classical representation of the network, and it was really hard to see, right? Because everything was grouped together helpfully. I mean, the package does contain a lot of algorithms for distributing your
Yes. Yes.
right that help you visually make sense of large sets of data. Not
Yep.
which complement, right? They don't.
Yep.
They only complement the things you're showing.
Yes,
there's
absolutely.
more to do with.
There's more. There's more. That's available inside the NetworkX package. Absolutely. There are also lots of research into drawing algorithms to draw networks in an efficient way. I'm not going to go through them. I'm actually personally not very well versed in that myself. There's the force-directed layout, which D3.js has implemented as well, and I've played with. But we all know JavaScript's a little bit of a pain in the neck to work with, so haven't really played any further beyond copying what's on Mike Bostock's webpage, right? So that's basically it. But yes, networks that are small enough, by all means, go use node-link diagrams. It's great because you can get a feel for it. But like I was saying, hairballs once you get to thousands of nodes. Like if you've seen those big ones, even if you color it, you can't really see clearly where the edges are being drawn, etc. And like I was saying, or like John Quackenbush had said, the heart of a network is in its edges, not in its nodes. OK, so with that, let's close up Notebook 2. And I'd like to have you open up Notebook number 3. And in this notebook, what we're going to do, so please run that first cell before we continue. Please run that first cell inside the notebook. So in this notebook, what we're going to do is we're going to try to look at the structure of the network. So previously, we had been interrogating, what's the edge list, what's the node list. Now we're going to look a little bit closer at the structure of the network and see if we can identify individuals that are important in this synthetic social network. So one may say that, so if we go to a networking conference, you might say that the butterfly networker is someone who is of great importance to this community because that butterfly networker is connected with a lot of people. He or she is talking with a lot of people at that conference and has a lot of links, a lot of relationships to other individuals. So one approach that we could use is to use a neighbors approach. We can ask and say, what we can do is we can ask, how many people is this individual connected to in a network? And so NetworkX provides a g.neighbors node with a parameter node function that lets us figure out the number of neighbors that a particular individual has. So I've listed here g.neighbors 9. We can do number 7, and we'll see that number 7 is connected to number 24 and 25. You can change that to 1, and you'll see 1 is connected to a different set of people. So what I'd like you to do, what I'd like you to try to do, is to create a ranked list of the importance of each individual based on the number of neighbors that they have. Right? And I've provided you with a few hints that you might want to use to tackle this problem. And when you're done, likewise, please give a thumbs up. OK, I see another thumb. I see another hand. I see another thumb. I see a fist. OK. Okay, I see another hand. Okay, I see another thumb. Just to give an overall feel, how many people are done? If you could just raise your hand one more time. Okay. Okay, so as I was mentioning earlier, because of time constraints, we're going to use a 40% threshold as a determinant to move on. So I think we're roughly at about 40% of the classroom today. So right now. So if you got something like this, it's not showing completely up here. Again, I'm trying to encourage you to use the list comprehension way of looking at it. And so we first get a list of nodes, but then we sort them by the length of their neighbors. And so I've used the lambda function. If you had an alternative way of looking at it, totally no problem. Like most coding problems, there's usually more than one solution that's feasible. But really, you should have 19 at the top. And if you got 19 at the top, then kudos to you, because 19 is the most connected inside this network. All right. So number of neighbors is one approach. We could also use the degree centrality approach, right? And so the degree centrality is actually based on the definition of number of neighbors. And the definition of degree centrality is the number of neighbors that a node has normalized to the number of individuals it could be connected to in the entire graph, right? Excluding itself. If you include self-links, then that's a different mathematical definition. If you exclude self-links, that definition changes. All right, so what we can do is we can get the degree centrality of the distribution of degree centralities by using this function called nx.degreecentralityg. Looks like it's stalled on me. Okay, let's try this again. So if you run that cell, you'll get, if you run nx.degreecentralityg, what it'll do is it'll return a dictionary, and the dictionary will show 0, the node ID, followed by that the result from that computation of its degree centrality, which is number of neighbors divided by number of total potential neighbors.
Is there anything beyond just the number of nodes in your graph?
Nope, that really is just it. The number of nodes in the graph minus, so depending on whether you include yourself or not, -1 or without the -1. So there are other measures of centrality. They're all implemented in the NetworkX API. They all have different mathematical definitions. And so what that means to your network analysis will change depending on what question you're asking. And so you use different measures of centrality, right? So it takes some discussion, thinking, and debate to figure out what centrality measure to use. In any case, I want you guys to do this. I want you to create a histogram of the distribution of degree centralities, and then likewise do the same for the distribution of the number of neighbors, and then create a scatter plot of the degree centralities against the number of neighbors. And if you're done with 1 and you don't want to do 2, you can skip right to 3, and that's totally okay. And because question 4 was answered, we're not going to go through that today. And if you'd like to, you could also compare your answer against the instructor notebook to see whether you got roughly the right answer. Don't forget, when you're done, please give a thumbs up. So just want to get a quick feel, how many people have done 1? Okay, great. And how many of you are attempting 2 right now? Okay, great. And how many of you are attempting 3 right now? Okay, great.
Three should be an exact linear relationship.
Exactly. And that's really the point. If you see, so let me just put this down, put this up here for you guys. It should be exactly linear, and that comes right straight from the mathematical definition. So all of this should just tie right back with each other, right? The mathematical definition of the degree centrality is based on the number of neighbors. So number of neighbors and degree centrality should be perfectly linearly related. All right. Now that we got that point out, that's great. We can move on to the next activity. So centrality by number of neighbors is a great way to think through who might be an important. Yes, sorry.
Do you mind going back and answering exercise 4?
Ah, yeah, okay. So exercise 4 is how many possible edges are there in total, assuming self edges are allowed. If there are n nodes, including yourself, and you're allowed to be connected to yourself, then there are n possible total edges. And then self edges are not allowed. And sorry, I mean this in an undirected network. So in a directed network, there's actually 2n minus 1 number of edges that are allowed.
From one node.
That's right. So from one node, edges that are allowed in a directed network could be I know you and you know me. So it's 2 per other node. But then if I know myself and I know myself, they're identical, then we take 1 out, right? So 2n minus 1. And then if self edges are not allowed in an undirected network, if there are n nodes, I exclude myself, there are n minus 1 people I could be connected with. All right? Okay. So now that we got this linear relationship out of the way, let's talk about paths in a network. All right, so graph traversal requires that you be able to graph traversal requires that you be able to trace out a path on the network. And it's useful if you're talking about message passing problems or infectious disease spread based on contact, you want to reconstruct things like that. One of the algorithms that's pretty cool is, how do you find the shortest path from one node to another node? And so if we draw that network, again, I'm breaking my own rules by showing it to you as a hairball. No, I'm not really, actually. It's less than 30 in size. So if we draw that, we'll notice that there are certain individuals for which, in the network, you could never draw a path to it from another node. And then there are other people who are connected with one another. And so we could draw paths. We just might not take, if we're not careful, we might not take the shortest path. Right, so how would you find the shortest path between 2 nodes? One approach is to take a breadth first search approach, in which you start at, if you say, I want to start at this node, and I want to get to a destination node, I'll search by looking first at the first degree of separation and seeing whether my destination node is there. And if it's not there, I'll iterate over all of the neighbors 2 degrees out and so forth and so forth. And so this is not necessarily the fastest, but it's the easiest to conceptualize. So that's essentially the approach. I've given you the pseudocode for that. What I'd like you to try is to implement an algorithm in a function called pathExists, node 1, node 2. You pass in 2 nodes, and you pass in the graph. And it should return a Boolean that indicates whether a path exists between these 2 nodes or not. And I'm going to break Pythonic conventions and say also print out whether whether a path exists or not. So don't just return true or false. Also print, it exists or doesn't exist. And so this notion of paths will tie into our idea of centrality in a moment. And I'm hoping that you'll follow me along with this. So I'm going to put back up, not the exercise prompt, but the pseudocode that you might need on the screen, just in case it's a little too far up while you're writing your code. I just want to reemphasize, if you've not been completing the exercises in time as we go along in the class, like I said, it's completely okay. These challenges, these are coding challenges. These are not mere coding problems. So they are designed to exercise the mind. Okay, I see a thumbs up. I see thumbs up, thumbs up. Thumbs up. Thumbs up. Thumbs up.
Is 3C, like, seems
Oh, yes, that's right.
in 2A, and I think 3C would be end as well.
Ah, yes, that's right. My apologies. Got the pseudocode wrong. Thanks for the catch. What's your GitHub handle?
Sava Amp
At Sava.
CAVA with a C.
Oh, CAVA, sorry.
CAVAUNPEU.
Okay, all right. Just a note for myself. Okay, so just want to get a quick feel for this problem. How many people are done? Please raise your thumb. Okay, we're at threshold. So if you got something like this, great. This is exactly a straight up implementation of the, yeah, it's a straight up implementation of the pseudocode. And if you do a test on, you do run a few tests, like I was mentioning, tests are important for your code. You should be able to see that path does not exist between 18 and 5 because they're not connected to anybody, and a path does exist between 29 and 26. All right. So I will admit this was a bit of a bait and switch. This algorithm has already been implemented in NetworkX, so you don't have, and likewise, a lot of these algorithms have also been implemented in NetworkX. So you don't have to implement a lot of these things yourself, all right? NetworkX has taken care of a lot of these things. So if you do haspath g185 nx.haspath, you get the same result there. All right. So shortest path is a function that we can use. It's different from haspath, right? Haspath is simply does a path exist. Shortest path is what is the set of nodes that I have to traverse through to get from one node to the destination node while hopping through a minimum number of nodes, right? And so it'll give us a list of nodes corresponding to one of the shortest paths. Of course, not all paths are guaranteed to be found, but that's okay if we're only interested in the shortest path. So what I want you to try to do is to extract just the subgraph that is induced from this set of nodes plus its edges, all right? And so as a hint here, so this function called g.subgraph nodes of interest is a useful thing if you're looking to only analyze a subset of nodes inside the graph. And that's why we call it a subgraph. So what I want you to try to do is to take 30 seconds to write a single line of code that implements this extraction, that extracts and returns this subgraph. And when you're done, please, again, give a thumbs up. Let me just check a few things. Right. Okay, so how are people doing with this? If you're done, please give a thumbs up or raise your hand. Okay, good. We'll wait a few more minutes. Okay, I see a few more hands. Great. right, just to get a feel for things. How are people doing? All right. Okay. We'll wait for 2 more hands. Just 2 more hands. One hand. Anyone else? Okay. I'm just going to quickly flash up the answer on the screen. What we've done is we've asked whether a path exists, we use the has path. And if the path exists, then we'll use the shortest path. We'll extract the nodes out, and then we'll get the subgraph of those nodes. All right. And then of course, if the path does not exist, then we'll put there, we'll raise an exception over there. All right. Yes. That's right. So if you extract the nodes, if you pass in the list of nodes, automatically it'll give you the edges as well.
How do you guarantee it is a path?
Pardon me?
So how do you guarantee the output here is a path? It could have a link between other edges.
So other edges, you mean?
Right. For example, between 4 and 14.
4 and 14.
So suppose there's an edge between 4 and 14. Will this be returned in this output?
Yes, it would. So if well, that's a good point. Let me close this presentation mode, and let's shortcut that. All right. Let's add an edge between 1 and 14. I'm going to forget about the metadata. And then we'll do that. So note the old one at the top, which didn't have that shortcut between 4 and 14. Note the new one in which I added a shortcut between 4 and 14. And so what's returned now is just 1, 4, 14 without all of the stuff in the middle. All right? All good? All right. Ooh, I'm going to have to restart my kernel now. No, I don't have to, actually. It's OK. All right. So in the interest of time, I'm going to skip over the following exercises over here because they're all about drawing stuff to screen. And so I'd encourage you to go back and look at them inside the notebook. There's also a challenge exercise in which we do a little bit more fancy math on the network. Go ahead, try that at home. We don't really have the time to cover it here, but that's totally no problem because they're all extensions of the fundamentals that we've gone through so far. So what I want to do is actually skip right down to the bottom and take a look at this notion of hubs being revisited. All right, what is a hub? A hub is not necessarily something that's connected to everybody. A hub can also be something through which messages have to pass through. It could be a bottleneck, right? A bottleneck, in some sense, is also a hub. So what I want you to try to do is to plot the betweenness centrality against the degree centrality for the synthetic social network that I've given you over there. So give that a shot. And so just to give you all the starting point, I think I've given you degree centrality equals something, and it should be a function called nx.degree centrality, if you look at the bottom of the screen there. I'm deliberately not scrolling up because I don't want to reveal the whole answer. If you look at betweenness centrality, likewise, you'll get the dictionary matched to, of nodes matched to its betweenness centrality. And the betweenness centrality, like I was mentioning earlier, is how many shortest paths have to pass through that particular node in the network. All right? So let me see if I can blow this up a little bit. Okay, degree centrality, betweenness centrality. Or you know what? Let me try go back to presentation mode. And zoom out a bit, zoom out a bit. Zoomed out a little too much. I don't want to dwell too much on this one. So if you didn't complete it, it's okay. The main point here is degree centrality and betweenness centrality are not perfectly related. And I'm just wondering if you might be able to think of an example where something would have high betweenness centrality, but not necessarily a high degree centrality. Pardon me. A bridge between two communities, perhaps. So yes, so exactly that. We're talking about a barbell graph, right? A barbell graph has two communities on the side, but there is an individual or a set of individuals in the middle through which if a message wants to go from one community to the other, it always has to pass through them. So this guy doesn't have a high degree centrality, but is still nonetheless important for the network. In some ways, this network is also brittle because if you remove that guy, then boom, the two communities are isolated. All right, so any other questions on this notebook? Pardon me? PageRank is also another centrality measure, absolutely. So Google's secret sauce is all based off centrality measures and graphs and networks and stuff as well. So it's also proof that networks have great applications in the real world. It's not just some theoretical thing that we're dealing with in this tutorial.
What's the case where you would have high degree centrality but not high betweenness centrality?
That's a tough one. I cannot think of one off the top of my head, but I can maybe try to imagine a structure where, say, one of these guys out here. So this one might have a, relative to the rest of the network, it's got a fairly high degree centrality. It's not the highest, perhaps, in that all of these are connected to one another. So actually, so this one would have a fairly high degree centrality, but its betweenness centrality isn't necessarily very high because messages don't always have to pass through that individual to get from this side to that side. That's sort of like a weak example, though.
Betweenness says the messages have to go through that person or can go through that person?
So betweenness is the number of shortest paths that pass through.
So perfectly connected network.
Perfectly connected network would have. That's a tough one.
But everyone's, in a manner of speaking, equally central.
Yeah. So that would be a tough edge case to qualitatively define. I'd have to think about that. Yeah. Okay, that's an example of how centrality measures can be used in different ways. And how different centrality measures have different interpretations in a real-world network. So with that, let's see. We're doing good with time. Let's jump over. Oh, yes.
So since the PageRank is going up, so does the network increment PageRank?
Yes, it does. It has the PageRank score for nodes inside a network as well. Okay, so with cliques, triangles, and squares, which is the next notebook, I only intend to go through the first exercise and leave it at that because the second exercise, the first exercise is sufficient to give you an understanding of finding structures in a network. All right, so let's open up notebook number 4 now. So in a network, in a social network, for example, if everyone knows everybody, that's a clique. That's the definition of a clique, right? If there's one individual in that group that doesn't know one person, then that clique is no longer a clique. So what you can think of is then the simplest clique is 2 nodes with bidirectional edges going between them. And the simplest complex clique would be a triangle, right? In a triangle, everyone knows everybody. Then you've got more complex cliques, which you have 4 nodes, and then you've got a whole lot of triangles inside there. So really, more complex cliques can be decomposed into lots of triangles. And so what we're going to do in this notebook is we're going to figure out how to write the code to find triangles in a network. And triangles have special meaning. There's geometric meanings. There's real-world social meanings, etc. We hope that most stable relationships are not marital relationships are not triangle relationships. So yes, there's special meaning to some of this stuff as well. So this really stems from the problem, and so sorry, let me backtrack a little bit. If you have an open triangle, that actually forms business opportunities as well. So if A knows B and A knows C, is it likely that B also knows C, right? And this is actually, if you combine this knowledge of the network structure with other metadata, what's the demographic information of B and C, etc., you can put a probability distribution on whether to recommend B to connect with C on LinkedIn. And that's actually, open triangles were exactly the way that LinkedIn started doing their colleague recommendation algorithms. Now they probably have something much more complicated than what I'm describing, but the core idea is there to look for open triangles. So if we skip that, what we're going to do in this notebook, just for this next 10 minutes or so, is we're going to look for triangles inside a network, all right? So the core idea, so how would you find a triangle, right? It's essentially a path traversal problem where you have to go 1 degree, 2 degree, and then 3 degrees of separation out from yourself and back to yourself, right? That's essentially what a triangle is. You have to be able to trace a path back to yourself 3 degrees of separation away. Or if you want to put it another way, then the neighbor, if my neighbors should include myself. That's another way of looking at it, right? The degree of separation isn't, it's also phrased in that particular way. So I'm a little bit unclear. Did I give you guys this code inside the notebook? Is this set of code present there? No, right? Great. So I'd like you to try to implement that algorithm then. And you probably, if you were fast enough, you probably saw that bit of code flashed up on the screen. You probably have an idea of the structure. If you didn't, then perfect. Please give it a shot. Let me see if, let me check that. I forgot what the prompt requirements were. In triangle, so it should return a true or false. And if we're done with this exercise, we'll be done with this notebook. I really would like to give you all a flavor for how we do statistical inference on networks in a bit, using hacker methods. So just a quick show of hands, how are people doing? Anybody done? Okay, we have a few hands done. I'm going to give it just 2 more minutes. This is definitely one of the tougher problems inside the notebook. It's not the toughest one is yet to come. But so I'm just going to give it a few more minutes. We don't have to have quorum on this problem to proceed. The core idea is if you know how to write a path traversal algorithm to find stuff, you should be able to implement this on your own. And you should then have the flexibility, really it's all about the flexibility and the mindset to be able to write your own code that solves graph problems, right? If something's not implemented, you should be able to take the API and implement it for yourself. And then hopefully also put in a pull request to NetworkX and then improve the package as well. Okay, I'm going to flash up the answer just really quickly. We have a node. I query for its neighbors, and I go 3. You'll notice I have neighbors 2 and neighbors 3. So it's a really inefficient implementation. You probably could think of a better implementation. This is the clearest way that I know how to present this concept in code. And so that's basically it. All right. And then we finally do the check. If I am in my neighbors 3 list, then I am in a triangle relationship with other people. But of course, what the meaning of that triangle relationship, that's a different thing. So like I was saying, NetworkX already has a function that counts the number of triangles. And so you can actually use that to say, am I in a triangle relationship? If it counts as 0, then you're not. And if it counts anything more than 0, then you are. This code above was simply for practice. OK, so we're going to skip the rest of this notebook in the interest of time. Before we move on, questions? Yes?
Is there a special significance for triangles as opposed to a more complex clique?
Triangles are the fundamental clique, in my opinion. Sorry, they are the simplest complex clique. So you can use triangles to query for higher order cliques, cliques that involve other nodes.
Are you saying that any higher order clique can be coupled with triangles?
That's my argument. OK, so we're going to skip the rest of this notebook. There are challenge coding problems at the bottom. Recently, I read stuff on how to do statistics for hackers. And so I'd really like to show you content that I've adapted to network statistics and how you can do statistical inference on networks. So notebook number 5 in the interim is a notebook that shows you how to load data from a CSV file into a NetworkX graph that you can start to play with. It's sort of, in my opinion, it's not the most important thing that I wanted to convey to you. So I've given you all of the code. You can modify it. You can change it for your own purposes if you ever have network problems that you need to solve in the future. So we're going to skip number 5 as well. So if you could please open up notebook number 6. Right? And of course, load, run the first cell so that we're going, run the first cell so that we're ready to go. So like I was mentioning, in this network, we're going to walk through a hacker's approach to statistical thinking, but now applied to network analysis. So I hope I don't have to emphasize this too much. Statistics really can be broken down into 2 things. One, descriptive statistics. So in other words, you've got a bunch of data and you need to summarize it for your boss. You give something like the mean, the IQR, etc. And then, but that's descriptive stats. And then there's inferential stats, which is basically saying this data that I observed, you either ask, what's the probability that it came from some random model? Well, actually, sorry, that's right. You are asking, what's the probability that it came from some random model? For the purpose of asking whether if that random model represents pure randomness that's meaningless, then you'd say it may or may not have happened by chance, or if that random model carries some particular mechanistic meaning, then you'd say, yes, my data fits this particular model of randomness. All right? So that's inferential statistics. So like I was mentioning, descriptive statistics essentially goes into this idea of, measures of centrality. And we're not talking about network centrality anymore. We're talking about net centrality of a distribution. So if you have a distribution of data, there's the mean, the median, the mode, and then there's variance measures, the interquartile range, the variance, and its square root, the standard deviation. If you're doing, and then there's inferential stats, which like I was mentioning earlier, it's all about models of randomness, hypothesis testing, or fitting statistical models. All right? So I'm not going to go into I'm not going to even mention it here. They're models of randomness. Please take a look at them for yourself. They're very useful to be familiar with. The only one that we're going to use today is the binomial distribution, which is what this synthetic social network was based on. So what we're going to do is we're going to test whether this synthetic social network came from a particular parameterized distribution of ER networks, Erdos-Renyi networks. All right? So just to give you an idea for the ER network basically works like this. If I have a set of nodes, then, and I put in a probability P, then every edge that's present inside there has the probability P of being existent. So we're flipping a coin, we're iterating over the edges, and we're saying, do we add an edge? Do we not add an edge? Do we add an edge? Do we not add an edge? And then we'll get some distribution of edges across the network. All right? So if you could read in the social network, the synthetic social network that I've provided, and just very quickly requery the number of nodes and edges. This synthetic social network, I'm going to spill the beans and say, yes, it is an ER network. It's the most convenient network that I could identify at that time. So if I have n nodes, so I want to pose this question to you all. Self edges are not allowed. If I have n nodes and m edges, and I assume that the graph came from an ER graph, what's a reasonable estimate for the value of P, right? So I've got some data, and I need to estimate the value of P in the ER model that likely generated my data. So what do you guys think? Back there. So the number of edges, average number of edges. Okay, all right, so that's a plausible answer.
You could do inference on a posterior beta distribution.
Okay, that's a bit more fancy. Okay.
Pretty similar to what you said, but more of a beta.
Yep, yep.
So it should be 2 over n minus 1.
2 over n minus 1. Okay, so I'm not going to give an answer just yet, all right, because this is all about statistical inference. You have your measure of p hat. So what I want you to try to do is to take a stab and guess what you think would be p hat. And write down your estimate for the value of p. Right? So like I was saying, I've given you the procedure for generating an ER graph. What's the value of P? And just to spoil the beans, right at the beginning of the instructor version of the notebook, I'm giving the wrong answer. And it's on purpose. Assuming self loops are allowed. Assuming self loops are allowed. So yeah, so work with your assumptions, right? That's a lot of this is statistics in action. So I have my answer. Don't copy it if you don't want to. You can copy it if you want to. If you had your own answer, work with it. Okay, so my answer, which is incorrect, but if you'll tolerate me for a few moments, my initial answer is m over n squared. All right, so going forth, the next thing I want you to do is to use the networkx function Erdos-Renyi graph to create a single ER graph using your computed value of p hat. So it would be, if you imported networkx as nx, you would do nx dot Erdos-Renyi graph. You'd pass in n, and you'd pass in p. And if you're familiar with statistics, this is exactly the binomial. It looks exactly like the binomial distribution parameters. And so make sure your ER graph has the same number of nodes as the synthetic social network. All done? If you're done, please raise your thumb. Okay, I see a few hands. I see another one. Okay, I'm going to just give you guys my answer over there. I'm using very generic parameters, so you can copy it. It's no problem. So the next thing I want you to do is to plot the degree connectivity distribution of the ER network that you've created and sort the distribution of degree connectivities from highest to lowest, and then plot this on a matplotlib plot. And in the interest of time, I'm just going to show you my answer. I want you to do it, and so you can copy it. And what I'm really trying to get at here is to get this idea of the distribution, the sampling distribution, out front and center. Okay, so if you take a look at that. Now, I went fancy with the matplotlib API, so legends, labels, colors, etc. You don't have to. For my incorrect value of p hat, you'll notice that the ER graph that I have doesn't follow the same degree distribution as the synthetic social network. All right? And so if you think about it, the ER network that you had created comes from a particular model of comes from a particular statistical model of how networks are formed, right? And the procedure I've described to you, iterate through every possible edge, and then flip a coin. How many is there? What's the probability of that? What's the probability of that edge existing inside the network? The space of all hypothetical ER graphs that could happen is the full distribution, and the space that you sample out is the sampling distribution, right? So if you look at Jake Vanderplas's slides, which I'm referencing at the bottom, statistics for hackers, the sampling distribution is sometimes hard to analytically define, but it's usually easy to simulate if you have a generative model like this. So just now, the ER graph that you had drawn came from one instance of the sampling distribution. So what I'd like you to try to do now is to, let's move on beyond this, figure out the sampling distribution of the mean degree of, so figure out the sampling distribution of the mean degree centrality from 1,000 tries or 100 tries samples of this synthetic network. So I'm going to give you the answer to the mean of the degree distribution, and then I'd like you to work on the next exercise below. And like I was saying, the mean that you get for your synthetic network might not be the same as the mean that I get, but I'd like you to just give that a quick shot. Yes, I'm intentionally giving you this so that you don't have to worry about futzing around with the NetworkX API. Sorry, the NumPy API in Python 3. There's a few issues, a few bugs there. The key line is this guy, and then you can do the analogous for the synthetic social network. All right? So if you move on, draw 1,000 instances from n equals 30, p equals your thing, your p hat value, and return the mean value inside there. How are people doing? Looks like we need a last-minute change of strategy. That's okay. So I'm going to basically show you I'm going to talk through the rest of this notebook in the interest of time. And then hopefully I'll have conveyed this idea of using a hacker simulation method rather than analytical math. If you're algebra blind like me, then the hacker method might be a more suitable way. So basically, what we're doing here is we're calculating the degree distribution over here. We're drawing 1,000 instances of the ER graph, and then we're figuring out the degree distribution, and then we're calculating the mean. We're storing the mean in the NumPy array, and then we look at, and so we have the distribution of mean values over 1,000 instances. If we plot that, you'll get something like that. And if you plot where the synthetic network existed, it's way out here. So it's quite likely, just visually, it's quite likely that we don't have this network coming from an n equals 30, p equals 0.05, right? But so this is like if you did the hypothesis test, the probability of seeing this would be very, very low. However, if you want to do model fitting, you might tweak the parameter p hat, and you might say, let's recalculate it based on some new formula, and then if you draw it, it's out over there. All right? And so what I'm hoping to convey to you all is that if you have a network and you want to calculate whether this network came from some particular model, go simulate 1,000 trials of that network and measure some statistic that you can compare, the distribution of the statistic that you can compare between the simulated trials and the thing that you've met and the network that you have, network data that you have on hand. Just to give you a few more references, a lot of this was inspired by this set of slides and this blog post. So please go up there and check it out. The final thing I want you to do is a little fun activity. So we've reached the end, but the one last thing I want you to do is this. There is a business card that's on the seats. I want to become a hub node as measured by high degree centralities. I want to be in triangle conference relationships with all of you all. So please write your name and email on the back of that card and then find someone to exchange that card with. All right? And if you have your own business card, go ahead. If you don't have the card, please pick it up. If you need a pen, there should be 2 Pilot G2 pens circulating around. If not, I can pass this around too. This was all about networks, so hopefully we got a chance to have you all network with one another as well. And with that, thank you very much.